Good morning. In this video, we are going to talk about the transformation of the absolute value function. So what is an absolute value function? The absolute value function is defined by this piecewise function. F of x is the absolute value of x is defined by x if the value of x is greater than or equal to 0, or negative x if x is less than 0. This sounds confusing, so let's break it down. Let us suppose that the absolute value of, let's say, any number, let's say 2, if we are following this definition, our x is 2, that's our x here. And since 2 is greater than or equal to 0, the absolute value of x is covered by this first part of the definition. So therefore, if x is positive or 0, we simply copy whatever is the value of x. In this case, it's 2. On the other hand, if we have a value that's less than 0, let's say the absolute value of negative 3, since our x in this case is negative 3, and negative 3 is less than 0, then we are going to get the negative of that number. So this is equal to the negative of this number inside, which is negative 3. So we get negative of negative becomes positive. So whatever is the x value here, the absolute value would always result to a positive value. And the graph of the absolute value function is given by this V-shaped graph. This line at the right side is covered by this first part of the piecewise function up to 0. And then the second part is this line at the left side. And let's note the following characteristics of an absolute value function. Its domain is the set of all real numbers from negative infinity to positive infinity for the x values. Its range is the set of all numbers greater than or equal to 0. So this is the range going to positive infinity from 0. Its graph lies completely above the x-axis. And its graph is symmetric with respect to the y-axis. Think of this as a mirror. The other side is a mirror image of the other side. So this is the parent function of the absolute value function. Now, let's look at the transformation guide for the absolute value function. The absolute value function can have this form: a times the absolute value of b times the quantity x minus h plus k. This k here will result to the vertical shift. If k is positive, it will shift the absolute value graph up. If it is negative, it will shift the parent function of the absolute value down k units. And then inside the absolute value symbol, the expression should be in factored form. And this h would represent the horizontal shift. In the ordered pair hk would determine the vertex of the absolute value function. So this point has a coordinate of h. Okay. Also, please note that the sign here is minus. Now, this factor b here represents the horizontal stretch or shrink. If the sign of b is negative, this will reflect the absolute value function across the y-axis. So this represents the horizontal reflection. While this A represent the vertical stretch or shrink, and if the sign is also negative, this will have an effect of reflecting the graph across the x-axis. Let's look at some examples. What you can see here is the graph of the absolute value function. So if x is 1, the absolute value of 1 is 1. If x is 2, the absolute value is 2. If x is 3, the absolute value is 3. What will happen to the graph if we add positive 2? If we have this expression, absolute value of x plus 2. Let's compare the green graph, which is the parent absolute value function, and the blue graph representing the absolute value of x plus 2. Notice that we still have the same shape, only that the graph is moved upwards 2 units. So what we have here is a vertical translation up by 2 units. That's the effect of this plus 2. Now if you make it minus 2, the graph is translated downwards 2 units. If inside the absolute value function we have a plus 2, it will translate the graph 2 units to the left, because we can rewrite this as minus negative 2. Minus negative 2. So x minus negative 2 is just the same as x plus 2. So let's put this back to x plus 2. So the absolute value of x plus 2 is similar in shape and size as the parent absolute value function, only that that graph is translated 2 units to the left. If we have x minus 2 instead of x plus 2, the graph is translated to the right 2 units. Think of this as sliding this green graph to the right 2 units. Now, if instead of adding or subtracting by a constant, we multiply the expression inside the absolute value function by a factor, let's say 2, notice what will happen. The effect here is, originally you have here x equals 1. By multiplying by 2 here, you get the inverse of 2, which is 1/2. So 1/2, that x equals 1/2 will have the same height as this one. Notice here that originally for the parent function we have x equals negative 1. If you get the reciprocal of this 2, that is 1/2. So get x equals 1/2, this is the point, and then trace it up. At this point, the y value is 1, and for the green graph, the y value is also the same. In other words, we have the same y value, only that we are compressing the x value from negative 1, we move it to 1/2. So think of that as compressing the graph to the center horizontally. And then notice now what will happen if we multiply by -2 instead of 2 to have the absolute value of -2x. Look at this is absolute value of 2x, and if I remove it and put the absolute value of -2x, you notice that you still have the same graph. That is because the absolute value function is an even function. So if you reflect it across the y-axis, you will still get the same shape and size. And then the next transformation is inside the absolute value function. If we subtract a constant, let's say the absolute value of 2x minus 4, this is the common mistake many students are committing, because you might be thinking of this 4 as the horizontal translation to the right. But notice that you do not move 4 units to the right. Rather, the graph only moves 2 units. Why is that so? The reason behind that is because this 2x minus 4 should be factored as 2 times the quantity x minus 2. And only after doing this factorization, when it is obvious that the translation to the right is 2 units, that's why you have this 1, 2 units translation. And then this positive 2 will again squeeze the graph horizontally by a factor of the inverse of 2, which is 1/2. And then if the number is outside the absolute value, like absolute value of 2x, this time the 2 is called the vertical stretch or shrink. If the number is positive and greater than 1, it will stretch the green parent function upward by 2 units. So originally your y is 1, then you double it. Originally here y is 2, then that should become 4 for this line, and so on. So we double the y value of the parent function. So if you have 10 here, for the blue line, it should be 20. The same is true for the other side of the quadrant. Multiplying the entire absolute value expression by a constant result to a vertical stretch or shrink. If the number is greater than 1, the result is a vertical stretch. If the number is between 0 and -1, it will flatten the graph. Notice that if I make this, let's say 0.5, the graph is flatter. If I continue making it smaller to 0.2, the graph is still even flatter. 0.1, 0.01, and it's almost a horizontal line. Now, what will happen if from 2x we make it 3 times the absolute value of x? The absolute value graph becomes narrower and narrower. Now, I want you to compare the graph of this 2 times the absolute value of x and negative 2 times the absolute value of x. Look at what happened. You have this dark graph at the upper part of this graph, and then the negative 2 reflected this graph backwards to form this graph at the bottom. That is because of this negative sign. And then when we combine all these different transformation, we have this. To say, what is the transformation of 3 times the absolute value of 2x minus 6 plus 2? So the first thing that we are going to do is make sure that this 2x minus 6 is in factored form. So we write that as 2 times the quantity x minus 3. These two graphs will have the same graph here, so you only saw. If I put this here, or remove that and chase it with another one, they are just the same graph. This plus 2, from here, it moves the graph 2 units up, 1, 2. And then this negative 3, this minus 3, resulted to the translation to the right by 3 units, 1, 2, 3. Therefore, the vertex now is at h positive 3, k positive 2. So the vertex now is at h equals positive 3 and k equals positive 2. And then these two resulted to the horizontal squeeze. That's why the graph is narrower than the parent function. And then this positive 3 resulted to vertical stretch. Thereby, the resulting graph now is this narrower graph. So let's do some examples here. If we have the absolute value of x minus 1, so the parent function is originally like that. That's the parent function. And then this minus 1 translated the graph 1 unit to the right. That's why we arrive at this red absolute value graph. Let's go to the other side. Y equals the absolute value of x plus 4. Again, from the parent function here, this absolute value of x plus 4 can be rewritten as y equals x minus negative 4 absolute value. So we are going to translate the graph 4 units to the left. 1, 2, 3, 4. And this red graph is the graph of y equals the absolute value of x plus 4. The absolute value of x minus 2. So this one translated the graph 2 units to the right from this parent function we translate the blue graph 2 units to the right, 1, 2, to result at the red graph. Notice that these two are similar inside the absolute value symbol, but there is a negative sign outside. It's the same as multiplying this entire expression by negative 1. This will have an effect of reflecting the graph vertically. So from this graph here, this red graph, think of that as you are folding the paper downward and you create a crease here at the x-axis. So the folded paper will result to this graph of y equals the negative of the absolute value of x minus 2. If we have this combination of transformation, you have a minus 1 here that moves the graph 1 unit down, and you have a negative 1 here that reflects the graph vertically across the x-axis. So the resulting graph is this red line. So think of that as originally having this parent function and then you move it down to this part by 1 unit because of this -1, and then you reflect it down to arrive at this red graph because of this negative sign. Then we have y equals the negative of absolute value of x minus 1. We graph first x minus 1. So from the parent function, we're going to move 1 unit to the right. So we'll arrive at this graph. And then this negative sign, we are going to reflect this yellow graph downward. And then because of this negative sign, we are going to reflect this yellow graph downwards to create this red graph. And then let's look at this last problem that we have here. So again, we need to factor this out. So y equals -3 times the absolute value of 3 times x minus 1 plus 1. So let's begin by drawing the parent function first. Then -1 here will result to a horizontal translation. So the blue line is translated 1 unit to the right because of this. And then this +1, we are going to move the graph upwards by 1 unit. So we'll end up here. That is because of this +1. Now this +3 will shrink the graph by a factor of the inverse of 3, which is 1/3. So in other words, we are going to narrow this graph by 1/3. So instead of 1 to the right, 1 up, it's going to be 1/3 to the right, 1 up, 1/3 to the right, 1 up, 1/3 to the right, 1 up, and do the same thing to the left. So we now have this graph. And then this -3 will result to reflection to the other side. But before we reflect, let's perform the vertical stretch. So we're going to perform this vertical stretch. So we are going to triple whatever is the value of y. So 1, 2, 3. 1, 2, 3. 1, 2, 3. So that is now the result by considering this +3. And then if we reflect this graph to the other side because of this negative sign, the resulting graph would be this red absolute value function graph. So that's how we perform the transformation of the absolute value function.